detections. This is very different than the last presentation that we did on hydrogen, which focused very much on explosive risk and the changes there between hydrogen and traditional hydrocarbons. We're now going to focus on CO2, which is more of a toxic risk. There we are, right. So we're going to go through the effects of CO2 on humans. This can also be extended to mammals, essentially, but we do have CO2 present by naturally in the natural lung composition. So while CO2 is about 400 ppm in atmospheric conditions, it's a lot higher in the air within our lungs. That's because it is a byproduct of combustion of respiration. So we do expect to see much higher levels, but the problems can arise when the levels get too high. So as we've mentioned here, it's about 380 ppm of CO2. That's actually out of date. It's now more like 411 ppm of CO2 in the atmosphere, and it's actually going up by 2 ppm every year now globally, whereas for the last 60 years, I think it's been around about the 1 ppm mark. So we're starting to see the increase of concentration in CO2 accelerating in a non-linear way. Pre-industrial revolution, it was sat around about the 300, so 280 to 300 ppm region. So since 1750, we've seen it go up by 100 ppm. CO2 has the greatest effect on breathing rate of humans. So this is essentially the body monitors the acidity levels in the blood. And as the acidity level goes up, it increases the breathing respiration rate to try and expunge more CO2 and essentially replace that with oxygen. The way that it works, CO2 is not like carbon monoxide. Carbon monoxide is an acutely toxic substance because it bonds in the same place on the hemoglobin structure as oxygen does. So it can oust hemoglobin's ability to carry oxygen. That's why it's so toxic. CO2 is not the same. It is not an acutely toxic substance, and we'll go into that a little bit later on. It does bind to the hemoglobin in some instances, but it's in a different place on the hemoglobin molecule structure. Mainly, it's actually carried in the blood plasma. And what it does is it moves through a chemical process where it changes into bicarbonate ions. And that's perfectly fine. It sits in the blood as bicarbonate ions, and then it is expelled once it goes back to the lungs, and the respiration continues. However, if there's too much CO2, we reach sort of the saturation point of bicarbonate ions, and it remains in the carbonic acid stage. It can't sort of transform through that chemical process. And if you are a process engineer, or you know anything about the movement of carbon dioxide, particularly through carbon steel pipe work, you'll know that carbonic acid is formed when CO2 and water come together, and that it's highly corrosive. So it can get stuck in that stage. Now, when your body is starting to recognize that the acidity level is going up, it will increase the respiration rate to try and purge that CO2. So this is the problem, is that if you are in an environment where the CO2 concentration is higher than what your body is typically expecting, that increased respiration rate actually pulls more CO2 into your system, and it exacerbates the problem. The more CO2, the quicker you breathe. The quicker you breathe in a high CO2 concentration, the worse the problem gets. Oh, we've already talked about this bit. So these are the EH40 levels for CO2. Now, when you're looking at EH40 levels for toxic substances, you'll be used to seeing things in maybe single or double digits. I think H2S is 5 and 10 ppm. Ammonia is, I really shouldn't have done this to myself, something like 10 and 25, I think. I'd have to check the document. So significantly lower than what we're looking at here, which is 5,000 ppm and 15,000 ppm. This makes a difference in the sense that you can actually talk about CO2 in volume percent concentrations in much the same way that you do with explosive gases as well, because the ppm level is so high. What we say here is parts per million can be an equivalent of percentage volume. Essentially, Percentage volume is divided by 100, parts per million is parts per million. So if you divide a million by 100, 10,000 ppm is 1% volume. That is a fact. You can apply that to absolutely anything. So it's exactly the same for hydrogen. 4% volume in air of hydrogen is the equivalent of 40,000 ppm. It just doesn't make sense to talk about explosive concentrations in anything other than percent volume, but the two can be traded, if you like. With toxic gases, we're often talking about ppm because we're looking at much, much lower concentrations. But you can see with CO2 that actually the two could be applied. This is a document from Occupational Health and Safety website. It's not linked because actually that's been taken down since I took this screenshot, but it does appear on other websites. RS Online actually has it. And one of the reasons why I want to show you this is because it's actually wrong. What we're going to point out here, 5,000 ppm is the short-term, no, it's the long-term exposure limit as per the EH40 guidance that I just showed you a second ago. They've missed out the short-term exposure limit, which should be in between 40,000 and 5,000. And they've also made this statement here, level is immediately harmful due to oxygen deprivation. That is incorrect. So it's important to know that sometimes the information that you'll find is not necessarily going to be right. When we talk about immediately harmful due to oxygen deprivation, that's akin to, say, nitrogen, where there's just not enough oxygen in the atmosphere. Nitrogen is not a toxic substance. It makes up 79% of air. The problem when you get exposed to a very a nitrogen atmosphere that has, say, 85% nitrogen or 90% nitrogen is that there's not enough oxygen left for you. That's not the case with CO2. CO2 is toxic in its own right. CO2 will have harmful toxic effects long before we reach the oxygen deprivation level. That's important to know. Why is that important? Because you should not ever measure for CO2 concentrations by using an O2 sensor, like what we traditionally do when we're looking at oxygen deprivation. That statement there, harmful due to oxygen deprivation, might lead somebody to think, right, well, I need an oxygen sensor. Incorrect. You need to be looking for CO2 when your target gas is CO2. The next level of examples of what happens to people as they get exposed to higher and higher concentrations of CO2 is taken from the DNV CO2 risk management guidance, which I can send out afterwards, after this presentation, along with the slides. We're not going to go through it all, but as we can see, 1 to 1.5% volume of CO2 is equivalent to the 10 to 15,000 ppm. This is the short-term exposure limit, and it should appear in between those 2 points here. And the effect of that can be seen here. Now, as we go through all of these, what we can see, and you can read these at your leisure, is that the time limit decreases as the concentration increases. So the length of time it takes for these harmful effects to take place decreases as the concentration increases. And a large part of that is to do with that increased respiration rate that we talked about in the beginning. 30% CO2 is 300,000 ppm, I think. Somebody's going to put that in the chat. So you can see that the levels that we're talking about are very, very high. We have CO2 detection in abattoirs because this is part of what is used often in the humane killing of animals. So they'll put them into a coma using CO2 and then finish the process, essentially. And that is why, as a byproduct during COVID, as a CO2 is a byproduct of loss of industrial processes, and then it is used in the meat industry or food and beverage industry. When those industrial processes slowed down during COVID, we weren't producing as much CO2, and that is why there was a meat shortage for a little while, because we didn't have the CO2 to continue those processes. So for some industrial processes, they do capture the CO2 already, and they then do sell that on to other industries. What we're talking about with carbon capture and storage is a huge volume of CO2 being captured, more than we can use in other industries, and therefore we treat it as like a waste product. And this is why the economics of CO2 capture is quite so important as well, with the carbon tax and things like that. So here's some facts about the gas. It's a colourless and odourless gas. It's 1.5 times heavier than air, so it really will sink down to the bottom. It's fully oxidized. This is why it's used in fire suppression systems, because you can blanket a fire with CO2. It removes the oxygen from the atmosphere, and essentially it's not reactive. It will not, it's not flammable at all, fully oxidized. Totally different than carbon monoxide, which I think is flammable at 15% volume in air. As we've mentioned, pre-industrial levels were 280 ppm, but our current levels, I need to update this slide. I think at last check, actually, they are about 411 ppm now. And this is the main point here. This dictates where you need to be putting your gas detection systems, because the CO2 is going to travel downhill. You can almost think of it like a liquid in the way that it will move. It will displace the air, it will move at low-lying areas, and it will linger for very long time. And if we go back to point 1, colourless and odourless, you would have no idea if you were stepping down into a trench that was filled to the brim with CO2. If it was a concentration that was more than 30% volume in air of CO2, which we can imagine would happen if you've got a 36-inch pipeline, as we're looking at repurposing pipelines that has a significant rupture and a significant release, you might have no idea, and that it can linger for extremely long periods because it's so heavy. So if I go back to the fact that we use this in fire suppression systems, there's an example actually of a fire suppression system that went wrong that was CO2 based in I think it's a West African country, but I can't remember which one it is off the top of my head. And what they did after that, there was a number of people who were hospitalized with that, but there was no fatalities. It must have had something to do with, I assume, oil and gas, because there was a helicopter nearby. And what they did was they got the helicopter to, in fact, let's get rid of that for now. It interrupts my story. They got a helicopter to come and hover over the area that was affected, and the downdraft of the helicopter, basically they used that to displace the CO2 that could be still lingering in low-lying areas for hours and hours after the event, essentially. So you might think if you have a big CO2 pipe rupture, well, we're totally going to know about that. Of course, the effects will be felt, the plant will shut down. But what happens to that CO2 that has been released? You can't see it, you can't smell it. So you want to be putting your gas detection in these low-lying areas. And this is something that the Acorn facility has thought about up at St Fergus as well. They've actually looked at the topography of the site and tried to locate the CO2 plant and compression station where you're most likely to get a leak because it's running at high pressure in a low-lying area on the full plant, as it were, because they don't want to put it on a hill. And then if there's a problem, have all the CO2 run down the hill essentially towards the office spaces. So some nice tables here of properties of CO2 that make absolutely no sense until you start to put them near a graph. So what we're looking at here, you've got your triple point with your CO2, as you'll probably know already, but if you don't, CO2 can't exist as a liquid at atmospheric temperature. It can only exist as a vapor or a solid at atmospheric pressure, sorry. So this is what dry ice is, if you're a frequenter of bars and cocktails. Essentially, if you take your CO2 to below minus 57, is it? Minus 56.6 degrees C, at atmospheric pressure, it'll do what we call sublimating, which is when it moves directly from a solid to a vapor, and that's why we get this lovely kind of like cloud of gas coming off it, and it makes a very dramatic effect. But once you move up past atmospheric pressure, you can start to store CO2 as a liquid. And then once you get up to a certain pressure and temperature together, we get what's called a supercritical liquid. And this is essentially where it's still a gas, but it behaves like a liquid, and it can be very efficiently moved through a process system. So this is the best way to move CO2. You want it to probably be around about 37 degrees. It's not that hot. And above 73.8 bar. Unfortunately, the scale on the graph and the table is not the same. So I have done like these handy comparisons for you. But yeah, you probably want to be around about the 75, 76 bar and 37 degrees C to move your CO2 as a supercritical liquid and get all of the benefits that that has. You obviously want to have it at a certain safety factor of safety above that critical point in both instances, because if for any reason you have a problem, there's a temperature drop or there's a pressure drop, if it's slight and you're hovering around that point, you're going to start to get phase changes within the pipeline. We know that's not good from oil and gas pipeline design. Oh, I don't need to send out the document. Right, this is the CO2 risk management. I knew I had it in here somewhere. And this is the level 3. They actually do levels 1 to 4. Level 1 and 2 is very generic. Level 3 has some really, well, level 1 and 2 are extremely generic. Level 3 is good. It's got what they call generic guidance in it, but it's actually really good and still very detailed. And then level 4 is even more detailed again. So all of this information is taken from this document. It's a lot of pages long, so I've tried to pick out the most pertinent points, but you can read it at your leisure by clicking on that link. So it's a good solvent, and essentially what that means, when it's supercritical, it can dissolve the greases that you would use to grease your pumps and compressors and things like that. Now you can get CO2 specific greases, so you would want to consider using those. I am not a process and pipeline engineer, but this document does cover a lot of this stuff. When it moves below that supercritical point, it loses its solvency capacity. So if it's just a liquid CO2, it's not such a good solvent. So if you have, for example, your CCUS plant is making blue hydrogen, so you are refining methane into hydrogen, and that methane, when it came aboard, had slightly a slight concentration of H2S. In its supercritical phase, that H2S will be completely dissolved in the process. You won't even know it's there. But if you move out of that phase, the H2S will be released in its gaseous phase from the liquid CO2. So you'll get like a concentration of H2S. One of the things that could cause that phase change is a drop in pressure caused by a leak. So you've got a leak, which has caused a drop in pressure, but it's also caused it to lose its solvency, which means that any impurities, for example, carbon monoxide, which is also part of the process when you are doing steam methane reforming, that's the first byproduct, and then they flood the carbon monoxide with oxygen to create CO2 because it's much less toxic. But it doesn't mean that you're going to get rid of all of that CO. You could get releases of these kind of toxic gases as well. And if the reason for your drop in pressure is because you have a leak, you've just got to be aware of that as well. We've talked about this. Now, just like humans, we need CO2 to live, as do plants. However, too much of it is toxic. So if you have subterranean pipelines running on your plant and you notice a loss of growth or plants dying, trees starting to look very unhealthy in a certain area, this has been observed in natural CO2 releases from near volcanoes, but also man-made subterranean pipelines as well. If you start to notice dieback, there's possible that you've got a subterranean leak and you want to look at that. I'm not going to go through this in massive detail because it's not my area of expertise at all, but this is all taken from that level 3 guidance. And essentially what it's saying is that CO2, as you move through the phase changes, can be very physically violent. So as the pressure drops, you start to get phase changes, you'll start to get temperature changes. Those temperature changes will then incur another phase change as well. So it starts to oscillate very much between these different phases of vapor, liquid and solid. Once we move past that sort of 73.8, I think it was, bar, it can then only exist as a solid or a vapor, and then you'll get really violent phase changes. This is something that was looked at in a study by Chinese University and the University of Lancaster, I think, which we cover in a little bit in a couple of slides' time. Oh no, it's this slide. So they did, I think actually, is this linked? Yes, I think there's a link down at the bottom here where you can actually get access to this study. And they did studies on the different accidental releases of supercritical CO2 from a pipeline, and it depended on the size of the hole, the leak hole, sorry, as to whether it created a visible plume, whether you got that solid vapor phase forming at the hole as well, which is then a visual indication. So although we talked about CO2 being a colorless and odorless gas, when it's moving from supercritical fluid or a liquid to atmospheric pressure, that extreme pressure drop can create that solid phase CO2. So you actually will be able to see a CO2 leak as it's moving through that state. Once the CO2 then moves through the solid state and sublimates straight to the vapor, you're not going to be able to see the vapor. And then that vapor, because it's heavier than air, is going to start to fall down. And this is why if you get a consistent and steady leak, you could get a real buildup of CO2 in the area because it lingers in these depressions. I think, yes, it's down at the bottom here. So if you click on this here, you can go through to this study. It's not a massively long document, but it is quite useful to look at what happens. One of the things that they noted here was it was the violence of the reaction. It had a physical impact. It caused a huge amount of vibration in their experimental process pipe work. And the DMV have also noted this as well when they've done their ruptures. That violence, that shaking and vibration as it moves through the phases could cause further leaks, which then causes more problems, essentially. Looking at the gas dispersion behavior, if you do have a leak, as we've mentioned, it's an extremely dense gas. It will displace the CO2. Again, this study is linked. Oh, it's the images here. So if you click on the images, it will take you to this study on the dispersion of toxic gases. It does deal with both carbon monoxide and CO2. This extract here is only focusing on the CO2, of course, but they've done some modeling to see, what's the most likely gathering of CO2 that's going to occur, and depending on the concentration and the leak rate and everything like that. So again, you can kind of see because of the topology, and if we have a large release, what's going to happen and how it's going to gather. You might want to consider depressions, pits, trenches, and then placing your gas detection in those low-lying areas underneath pipe work and things like that, because that's where the CO2 is most likely to gather to. And because it's a heavy gas, it will be affected by wind and weather, but not as much as light gases, which diffuse very, very easily. This is obviously something that we talked about a lot with hydrogen. This is the well-known video. Again, you can click on this link here. This will take you to the video, which is the large-scale pipeline rupture testing that was done by DMV at Spade Adam, which is a research site on the RAF Spade Adam base. You can see, well, if this is a CO2 release, like, why can I see so much of it if it's apparently an invisible gas? What this is, part of it is the CO2 sublimation and the visible vapor, but a lot of it is the temperature causing the water vapor in the air to become visible. So it's quite hard to distinguish between what is CO2 and what's water vapor there. They've noticed some concerns. Again, I think you can go onto their website from the link to that video and read the wider report on this. But they said that the area dispersion was larger than expected for the volume of CO2 released. And of course, once it's moved into its vapor phase, its gaseous phase, sorry, it is now colorless and odorless, and it will linger. This is the point here. It risks running fractures due to phase changes. This is what was mentioned on a smaller scale in the report done by Lancaster University, along with the Chinese universities. This physical violence of a leak and how it can then exacerbate the problems and have a physical impact on the damage to the pipeline. So what they did this testing. This was a number of years ago now, but what they wanted to do was to update the guidance that was given for CO2 pipelines, given that we're now looking at CO2 pipelines on a much grander scale. One of the other areas where Draeger has CO2 detection is in breweries and a lot of food and beverage plants, but these are all relatively small sort of process pipeline. We're not talking about the big high pressure pipelines where we're looking at reusing parts of the national grid infrastructure where the volume of CO2 really could be significant. So the original guidance was published in 2010, which is, if you click on the link down here, that's available. They've now updated it. That was published in 2021, and a lot of the research from this testing here has been included in that. So design and operation of carbon dioxide pipelines, you can read that document by clicking on the link down at the bottom. So we've talked about the gas. let's talk about the gas detection. So just as a reminder, we've got the long-term 8-hour time-weighted average or limit of 5,000 ppm and 15,000 ppm for the short-term 15-minute period. So this is again what I mentioned with the hydrogen slide. I think you've got primary and secondary gas detection, and point detection is your only primary means of gas detection. I know that line of sight has become more and more prevalent as we move through designing of fire and gas systems, but you can't have a fixed gas detection system with no point detection. You can have a fixed gas detection with no line of sight gas detection. So you really need to focus on point first of all. This is the Draeger point gas detection. We've got a device with a screen, Polytron 8720. This has full heart capability. It's the premium device, and you can sort of go down from there. PIR 7200, which is exactly the same IR sensor, but it's got no screen, which makes it slightly cheaper. And then we've got what we term the remote sensor arrangement as well. So because the PIR 7200 is a blind device, apart from there's a little indicator LED that'll tell you if the device is in fault, you can put that down in low trenches. But if you want to have a device with a screen so you can see the concentration, but you need the sensor to be in the target area, you can do what's called a remote sensor arrangement, place the sensor down in the low-lying area, and then have the screen at the area where people are likely to frequent. I think the max distance on those is like something like 30 meters. But you probably wouldn't need it that long. It's got a different filter on it, this one, so it's exactly the same sensor as what we use for our infrared flammable gases, but we're looking for a totally different wavelength, 4.2 micrometers for the gas, which actually is not dissimilar than the wavelength we look for the CO2 byproduct of flammable gas combustion, which is 4.3 micrometers. So of course, this is toxic, just toxic gas, so there's no flammable risk. We want to mount it 18 to 20 centimeters above the ground. Ideally, actually, you'd mount it on the ground as low as possible. However, we have to think about the practicalities of installation. So there's a lot of dirt, rain splash and in external environments, even in things like breweries. We still recommend this because in like big warehouses, even somebody walking across the warehouse can kick up dust, and that dust can then start to impact the sensor because it's an optical sensor. It's sending out an infrared beam through glass onto a mirror and then rebounded. If you're on the hydrogen webinar, I think I went through that just in terms of how it works. For flammable gases is exactly the same. We're just looking for a different wavelength, this one. So yeah, you end up with a high maintenance burden if you mount them very low down, because you've got to clean that glass, you've got to clean the mirror. It's all these dirty particulate bits sort of get in and about the sensor. The main difference with CO2 versus methane is that there's always a background concentration of CO2. We've got the atmospheric concentration that we have to take account of. And we've got that at 380 ppm. And obviously the background concentration of atmospheric CO2 is going up all the time. So I might actually have to ask our research department if we need to change that. But we do have a factor of safety built in significantly. So it actually probably won't make that much difference if we're looking at 40 ppm difference. We don't have a background concentration of methane to take into account because we're not expecting flammable gas to be there all the time. So this is one of the differences. We have a minimum recommended alarm threshold, which we set at 1200 ppm for CO2. This is calculated by, we actually have the minimum that we can detect CO2 accurately at, we're in a laboratory condition at 190 ppm. That's the minimum that we consider to be accurate. What we do is we add a safety factor of 4, so that gives you 760 ppm, and then we have to take account of that background CO2, which gives you 380 ppm, which is 1,140 ppm in total. So if we the minimum accuracy times 4 plus background concentration, and then we round it up a little bit more for safety. So we say below 1200 ppm for CO2, you're not going to be able to detect it accurately. In fact, when we've provided CO2 monitoring systems for diving vessels. This is we have oh gosh, what's it called? Draeger's orb, and it's this carbonate type pellet stuff which we put into diving vessels, which which like cleans the CO2 from the air that divers are rebreathing when they're living in their diving chambers for like 3 months at a time. And so we sell that, but we also sell the gas detection to monitor the system and check for the accuracy of that CO2 concentration, make sure it's not getting too high. On that system, they designed one which safely used a factor of safety of 2, in fact, rather than a factor of safety of 4, and it was still accurate. But we really do err on the side of caution with Draeger. So you probably could go lower than that if you wanted to. However, that long-term exposure limit of 5,000 ppm, you can see that 1,200 ppm is still well below that 5,000 ppm short-term exposure limit. You may or may not be aware, but IR devices are non-linear. So if you have to select your point at which you want to be accurate, and the higher that is, if you have a high accuracy point, we want to be really accurate at a high concentration, you will sacrifice accuracy at the low concentration level. And the opposite will also be true. If you go for accuracy at low concentration levels, you will get less and less accurate at high concentration levels. This is what Draeger have done. We have foregone accuracy in high concentration levels to be accurate at low concentration levels. If you check the GD10P, there's a CO2 version of that device data sheet. It states, I believe, that it's the detection limits on it are 1% volume. And if we go right back to the start of my presentation, 1% volume in air of CO2 is 10,000 ppm. And on the data sheet, it appears like that is their lower detection limit. If it's lower, they need to change their data sheet because otherwise it's a little bit confusing. Whereas we've gone for accuracy at 1,200 ppm, so significantly lower. However, the GD10 will be more accurate at high concentrations than our device. Our deflection of linearity at the high concentrations is higher. It's just, the compromise that you make. You make your choice. Where do you want to be accurate with an IR device? Oh, I mention it here. Yes, so these are the full-scale deflections comparisons between the 2 devices going off the data sheets. They don't directly compare, like we've both kind of written it down differently. But you can see at 0 to 30% volume, we have 4.5% volume, sorry, and we have 0 to 30% deflection. And that's significant, and we don't even put a limit after that. It just gets worse and worse and worse. But we've kind of figured that if you want to measure the high concentrations of CO2, you're going to need to look at a different device. We're very much looking at the toxic risks. So as I mentioned, you need to use point detection for any gas detection system, whether flammable or toxic. You have to have that primary detection, but you can put in secondary layers of detection, and one of those is line of sight, and you can use this for toxics. Now, full disclosure, Draeger do not have an open path CO2 solution. We do have one for H2S, and we have one for ammonia as well, both of which are, well, ammonia is a light gas. We don't have CO2. There's some things you need to take into consideration when detecting toxic gases, any toxic gas, not just CO2, with line of sight gas detection. I don't know if you recall on the hydrogen presentation, but open path gas detection can only give you, because it's covering such a long distance, it can only give you an average concentration across the beam path length. Can't tell you where that concentration is along the beam path length, and it can't tell you if it's got a large, low concentration gas cloud or a small, high concentration gas cloud. It's just counting the photons that have deflected a certain amount of energy between the transmitter and the receiver. And it can't tell you if those photons, there's 100 of them spread out, for example, or if there's 100 of them really close together. Now, for flammable gas, you can err on the side of caution, and it's the size of the gas cloud that's the problem. But with toxic, it's the concentration that's the problem. And so you really do need to know, if you're using this as a safety system for toxic reasons, how concentrated that amount was and where it was, because somebody stood at the transmitter end of a 40-meter beam path length and somebody stood at the receiver end, one of them's going to have been exposed if you've got an alarm level concentration, but you don't know. Well, actually, they might not have been exposed. It's hard to tell. So you can see that for that reason, open path is not the best for toxic. However, if you're looking to monitor a leak and you want to cover a large area, it can work for that. The other point to notice that because CO2 in particular is a heavy gas, you're going to have to mount these devices low down. As we talked about, there is it's 18 to 20 centimeters off the ground, ideally. So, and you're probably going to want to put those in trenching under pipelines, for example. So you're just going to have to be aware that if it's in a low-lying area outside, you're going to get a lot of rain splash, a lot of dirt. You know, these devices, when we have methane devices that are mounted at height, sometimes sort of 5-10 meters in the air, there's already kind of, oh, you know, we have to clean the lenses and we have to then realign them after we've cleaned the lenses because they're getting dirty. These devices are going to get even dirtier. There's a lot of dirt sources around here. You've also got the potential of foliage growth at low level as well. Even if it's in a concrete trough, mud can get washed down there by rainwater. Then you'll just start to get plant life growing. It could interrupt the beam. So just, again, something to be considerate of when selecting open path gas detection for CO2. These considerations are just something that you're going to have to be aware of. And like I say, we don't have it in the portfolio, like full disclosure. And oh, I've just talked about this. Yes, so small concentration gas cloud, high concentration or large concentration, large size gas cloud with a low concentration, it can't tell the difference. I'm just going to skip over this because I'm conscious of time. We've talked about it already. This is where this health and safety report is where that 5-meter gas detector spacing came from. You can still use 5-meter gas detection spacing for toxic gas like CO2. It's kind of useful, but it came from a flammable consideration, essentially, because they were considering overpressure. That spacing has proved itself over the years, like it will, you know, the dispersion of the gas is likely to reach a detector within the 5-meter range. So it's still useful, but it's just to be aware that that was set for flammable gases. And the reason for that was because of the overpressure created by a certain gas cloud size when it explodes. CO2 is not explosive, so we don't need to consider that. But if you still want to use it, it means that a 40-meter beam path length, you would need, if you were going to use point detection instead, 8 point devices. The cost is roughly comparable, to be honest, although maybe not if you consider all of the cabling that has to go into place there. But if you're looking at it from a safety point of view in terms of toxic exposure, point detectors would be able to tell you where in that area that concentration was and how much was there, as opposed to it being kind of undisclosed because it's just an average across a beam path length. So you can also use open ultrasonic gas leak detection for CO2 as well, because it's just listening for the sound of a leak. So this is another way that you could use secondary detection in order to fill that gap that is left by point detection in terms of area coverage. If you were on the hydrogen webinar, you'll know we covered this already, how the device works, but essentially it can hear sound frequencies above the human hearing range at 20 kilohertz. And it's a very good way of getting an immediate response to a gas leak because it's traveling at the speed of sound. Essentially, you don't have to wait like you do with point gas detection for a certain accumulation to gather. And that time, one of the things, so we talk about T90 time with gas detectors, that's the time that it takes for the detector to respond to 90% of its target concentration, but that presumes that the target concentration is at the sensor already. It doesn't take into account, because how could we possibly know with different wind directions, different ventilation, sort of styles, different strengths of that ventilation as well, how long and where the leak was in relation to the gas detector, how long it was going to take for the gas from the leak to move to that gas detector. You just can't predict that. Ultrasonic gas leak detection can take that out of it because it just, the sound of the leak travels at the speed of sound. What you do need to do is put a delay on these devices, as we've mentioned before, because you do have what we call friendly fire when it comes to leak noises. Compressors, pneumatic actuators, pressure relief valves will all create some kind of leak noise. What we expect, though, is that these will only issue that leak for maybe a couple of seconds and then it will stop. once the pressure relief valve has lifted, and then it has righted the pressure and then dropped again on its bellows or its spring, whatever it is, you're going to have that noise removed, and we're not expecting that noise to be sustained, whereas a leak would be generating sustained noise. It's also important to mention that this is noise outside of the band of human hearing. So a pneumatic actuator, for example, as the piston moves off its seat, you've got a teeny tiny window where it's replicating a pinhole leak, which is what this device is listening for. As it moves past that point, it then moves into the audible sound of hearing. So what you can hear is not what this can hear. So if you can think, oh, well, pneumatic actuators, it sounds really loud for like 10 seconds. It's listening for the equivalent of a pinhole leak, which is the tiny gap as the piston moves off the seat. Once it moves into the audible hearing range, this device is not interested in the slightest. So it's listening for a very particular kind of sound. And if you set a delay time on it, typically rule of thumb is about 6 seconds, but you're best to do like a sound survey to really figure that out. You would then be able to eliminate, specific to your site, post-survey, what noises are friendly fire and what noises are they're just, that is a leak that is of concern. And again, you think, well, if it's so fast, but now I've had to put a delay on it, what's the point? Like I say, it can take minutes for gas to move from a leak source to a point detector or to an open path gas detector. We know this. And then it has to reach the sufficient concentration to get your alarm set point. And the windier and more turbulent that the atmospheric conditions are, the longer that's going to take, whereas this device is not affected by those conditions. It does depend on pressure, so this is not going to work in your carbon capture area where you've done your, say if it's amine capture, that's usually typically a very low pressure system. There's no point putting UGLD in a low pressure area. It needs at least 4 bar to work, or 10 bar it says here. And you need to, so you would put this in the high pressure area, so like the compression station before the CO2 is going to be moved into a long distance pipeline and moved a long distance. If it's low pressure system, there's no point putting UGLD in there. As we've already mentioned, it's not affected by weather so much. And actually here is where you're looking for CO2, toxic gas explosion. So we're not concerned with the vapor cloud forms and ignites. This is where the traditional point detection has an impact here by comparison to UGLD, which is responding here. In fact, with toxic exposure, you're all the way down here in the event tree. So it's even further away, and UGLD can respond even more rapidly. Does have some limitations, and all gas detectors do. There's no such thing as a perfect gas detector. Just like I mentioned with the linearity error for IR, you've always got to make your choice. With open path, you might be able to cover a larger area, but you're going to sacrifice accuracy. With point detection, you're going to get accuracy, but you're going to sacrifice area coverage unless you want to spend a lot of money. UGLD, there are some limitations. It's not gas specific. As we've mentioned, there's a lot of friendly fire on site, and false alarm immunity must be set up specific to the site. However, it's very good in outdoor applications. You get that fast response. You don't need to wait for the accumulation, and sometimes it not being gas specific can be a benefit because it's looking for all leaks. So if you have a device that's set up because you've got a hydrogen and CO2 on your plant in the same area, you would set it up as you would for any other device to the target gas where it has greatest sensitivity, and then it would be able to hear for a leak in either of those systems. I'm just going to skip through this because I'm conscious of time. This is a calculator where you can we can figure out the distance that would be covered by a device. So in here, I've actually put carbon dioxide. I've put the conditions to be roughly that supercritical fluid type, and a leak size of 2 millimeters. You would need to determine through your own safety case what leak size you were going to be concerned with. And leak rate is calculated from the leak size and the pressure. So again, if you have a target leak rate that you want to detect below, you'll need to tell us that because you guys are the experts in your process system. And then it will spit out an area where we can see how far away the distance can be covered by that device. So this is something that I just want to discuss with you guys briefly. This is not able to detect CO2 at the moment. This is actually a methane's emissions monitoring camera. It works on infrared. And we are using this a lot in the States at the moment because they have the new LDAR emissions regulations where I think the way that it works, they've assumed a certain emissions level from plants, and then it's the plant holder's duty, and so they pay a fine on that emissions level, and it's the plant holder's duty to prove that they have an emissions level lower than that and therefore reduce the fine. I think that's a very simplified way of the way that it works. And so they're using these methane emissions gas cameras to kind of prove where they do or don't have leaks and things like that. And of course, with methane emissions causing global warming, I think it's something like 80 times worse in the first 20 years than CO2, the impact of methane versus CO2 emissions as a greenhouse gas. We're trying to prevent more and more methane emissions from plants as well. However, because it works on infrared, this device could be moved onto CO2. We haven't done it yet, but it's something that we're talking about. And therefore, it could pose as an alternative to open path CO2 gas detection in terms of the area that it can cover. One of the things that's quite good about this device as well, when we look at it for methane emissions, is that it covers up to 30 meters in depth. It can go further actually, but in terms of safety, we sort of say 30 meters distance. For emissions monitoring purposes, actually, we're doing some testing at the moment and it could be pushed out significantly further than that. But 30 meters is what we say for safe applications in a safety system. So traditionally, this is looking for methane emissions, and it has an alarm level, an A1 and A2, just like any other gas detector, as it were. And what it does is it looks at each pixel. It has a pixels, and it is looking for a temperature difference between the background ambient temperature and then the temperature of a gas release. And it can tell you in which pixel the gas is not only present, but it can tell you a concentration. And if it's on a safety system, it can tell you A1 or A2 alarms have been reached. But if it's just looking for emissions monitoring, it's sort of open scanning. So we could do, in theory, larger distances with this, and it could tell you exactly where that CO2 emission is coming from. I will send a link for this device in the chat when we share the presentation slides as well, so that you can kind of watch a video and see actually how it works, because I don't think I've really done it justice here. But as I say, this is not currently able to do CO2, but because it works on an infrared-based principle, we could pivot this onto CO2 with some R&D, and it could give that area monitoring, large distance area monitoring that OpenPath gives, but with the accuracy of actually being able to tell you concentration and where in that area that leak is coming from. And again, if we start to see emissions regulations coming in for CO2 pipelines as well, because there's no point capturing that CO2, doing all of the fiscal part where we're sort of metering CO2, we're paying carbon tax credits and all the rest of it, only for it to be leaked further down the process and that go unknown. They could bring in CO2 emissions monitoring targets as well, just like they are looking at for, they have brought in for methane in the US, and they are looking at for methane in the EU. So this is something that we could potentially put some more R&D in and pivot it onto another gas. So I thought it was worth sharing, and I will share the link to the video. And I think that QR code won't work. I still didn't change it, sorry. But you can find me on LinkedIn if you want to connect with me here. And we've got a little bit of time for questions.